music. In the name of Allah, all praise is due to Allah, and peace and blessings be upon our Prophet Muhammad, his family. Now moving on, O Allah, there is no ease except what you have made easy, and you make ease determination and sadness, O Lord, if you wish. In the previous episodes, we discussed low impedance differential protection in the case of a single transformer and explained the fault conditions. Then we moved on to the situation with a single circuit breaker. We explained the fault conditions, and then we transitioned to the single bus bar. Of course, in this case, we have a circuit breaker and discussed the fault conditions related to it. Then we moved on to the single bus bar, and the cable circuit breaker with only one city, and on the circuit breaker page with only 1/6. Then we explained the fault conditions on the double bus bar used in high voltage substations. At the end of the episode, we discussed end voltage protection, noting that bus bar protection and end voltage protection are usually found in the same relay, such as the ABB Rebi 500 relay. In this episode, we will explain high impedance differential protection in detail, so stay with us. Some of them are noticeable. Subscribe to the channel. In episode 10, we discussed high impedance differential protection. This episode focuses on bus bar differential protection schemes and optimal adjustments for high impedance protection. Due to errors from high differential currents, backup protection, the check zone confirms tripping decisions and prevents maloperation if the discriminative zone is triggered. Differential protection, identifying fault locations, is known as the discriminative or main zone. Frequent operational errors due to high differential current from issues like open circuits in CT circuits or auxiliary contact problems necessitate backup protection to confirm tripping. This backup, called the check zone, prevents maloperation if the discriminative zone activates. A specific CT feeds the check zone on each bus for all feeders, except bus sections and couplers. This CT is independent from the one used for the discriminative zone, so each bus has two CTs, one for the discriminative zone, one for the check zone. We use backup protection to verify the tripping decision, called the check zone. This check zone helps avoid any error in differential protection if the discriminative zone is activated. A CT is installed to feed the check zone on each bus for all incoming and outgoing feeders from the station, except for the bus section and bus coupler. This CT is independent and different from the CT used for the discriminative zone, so each bus has two CTs, one for the discriminative zone and the other for the check zone. The check zone calculates the differential current value for all bus bars as if they are one single area, monitoring the entire system at once, but does not identify the exact fault location. In contrast, the discriminative zone monitors a specific task only and accurately identifies the fault location in any zone. The check zone monitors the entire system as one area, calculating differential current for all bus bars, but doesn't pinpoint faults. The discriminative zone, however, focuses on specific tasks and accurately identifies fault locations. In the bus bar protection single-line AC circuit image, each bus has a CT for both zones. The CTs at the bus bar protection circuit breaker ends overlap for the discriminative zone. Secondary CTs combine with supervision, high impedance, and metering in bus wiring for each zone specific to Zone A, Zone B, and the check zone. The discriminative zone identifies faults on bus bar A or B, while the check zone sees faults on both as one bus. The secondary CT is combined with the supervision, followed by the high impedance and metering on what is called the bus wiring for each zone. Therefore, we will have specific bus wiring for Zone A, specific bus wiring for Zone B, and specific bus wiring for the check zone. The discriminative zone can identify whether the fault is on bus bar A or bus bar B, while the check zone detects a fault on bus bar A and bus bar B as if they are just one single bus. And we want to highlight a very important point, which is that the check zone can be used with both high impedance and low impedance differential protection. It is not limited to just one specific type. Subscribe to the channel. The revival of a nation. For the bus bar protection to trip, the differential protection must operate on both the discriminating zone and the check zone simultaneously, and this can be expressed in control circuits by connecting multiple contacts in series, as shown in this circuit. Notice that the contact for 87A, which represents the discriminating zone, will pass through the contact for 87, which represents the check zone, before going to the trip relay. In some bus bar protection schemes, the 87.8 is placed on the negative side, meaning it is a condition for the negative to reach the trip relay, while the 87A is placed on the positive side, meaning it is a condition for the positive to reach the trip relay. Then, with a bus bar lacking a circuit breaker, city secondary connects to high impedance bus bar protection via city switching using ABBRX MPV4. There are relays for bus bar 1A and 2A protection. The bus bar check zone calculates currents if a machine is out for maintenance or fault occurs. Then, select an option from the bus bar selector switch. This creates a bypass on the relay output contact as it hasn't operated due to maintenance or fault. If city secondary circuit opens accidentally, CT supervision conditions the CT secondary circuit and bypasses the relay output contact. This cancels the relay operation associated with the opened CT circuit, termed CT unhealthy. You can bypass the output contact of this relay as it hasn't operated due to maintenance or fault. However, if there's an accidental opening in the city secondary circuit, the CT supervision will create a condition and bypass the relay output contact. This cancels the relay operation for the open CT, termed CT unhealthy. Bypassing both zones bypasses both output contacts, meaning the CT supervision will create a condition and perform a bypass on the relay output contact. This cancels the relay operation for the open CT, termed CT unhealthy. The statement applies to both discriminating and check zones, leading to a problem. An out condition on both zones bypasses the output contact, causing a false trip. Simultaneous faults result in false trips. We modified the check zone circuit to block negatives from the tripping relay if all relays are out or CTs are unhealthy. This was done by adding signals from both sides cause a false trip. Similarly, simultaneous faults on both sides cause false trips. We modified the check zone circuit to prevent negatives from reaching the tripping relay if all relays are out or all CTs in the discriminating and check zones are unhealthy. This was achieved by adding a normally closed contact in the check zone panel. However, a new issue arises. If one relay is out with a healthy CT and another is in with an unhealthy CT, a signal from one side causes a false trip. In this problem, we modified the check zone circuit to prevent the negative from reaching the tripping relay if all relays were out or all CTs in the discriminating and check zones were unhealthy by adding a normally closed contact in the check zone panel. However, a new issue arises. If one relay is out with a healthy CT and another is in with an unhealthy CT, a false trip signal can occur. The differential protection relay should not operate without conclusive busbar fault evidence due to two doubts: the discrimination zone being out of service and the city secondary for the check zone being open. Thus, conditions need adjustment. If one relay is out with a healthy CT and another is in with an unhealthy CT, a false trip signal may occur. The differential protection relay should not operate without clear busbar fault evidence. Two doubts exist: the discrimination zone is inactive and the check zone's city secondary is open. Conditions must be readjusted to prevent unnecessary busbar protection tripping. The diagram should ensure a resistor in parallel maintains a negative on the trip relay coil, preventing corrosion and keeping the relay ready. This table shows the 1.32 operating philosophy against busbar protection under various conditions, addressing incorrect operations. It presents 9 scenarios with 5 requiring a trip signal. To ensure that the busbar protection tripping relay does not operate in this case, the final diagram should look like this. The purpose of having a resistor here in parallel is to maintain a negative on the trip relay coil so that this coil does not suffer from chemical corrosion over time. This is because this particular protection may not operate for a long period, and in this way, this relay or this protection remains in a state of readiness and constant activation. This table illustrates the operating philosophy of 1.32 against busbar protection under different operating conditions in electrical stations. It has addressed most of the incorrect operating cases for busbar protection. This table was derived from the final circuit that was created in the busbar protection scheme. In this table, 9 operating scenarios are presented, 5 of which should trigger trip signal, and 4 of them should not trigger a trip signal from the relay, which you can study in detail yourself. The high impedance differential protection relays come in 2 types. The first type is called voltage calibrated relay, while the second type is called current calibrated relay. The voltage calibrated relay has multiple tabs ranging from 25 to 175 volts, with each step being 25 volts. Relay 25 175V, 25 325V, 15 180V, steps 25V, 50V, 5V, no external resistors. Or it can range from 25 to 325 volts, with each step being 50 volts, or from 15 to 180 volts, with each step being only 5 volts. Additionally, there is no need to install any external resistors with this type of relay because the relay already has a high resistance. To determine the voltage current setting, it is necessary to know the relay operating current for each tab. If the relay operating current is low, a shunt resistor can be added to increase its value. Examples of this type of relay include MFAQ 14 or 34. Notice in this table that as the relay voltage setting increases, the relay operating current will also increase. The second type, the calibrated relay, has a low fixed value, only reaching 1 V. A high resistor is added in series with the relay coil, the stabilizing resistor, to form a high impedance relay. Multiple tabs are based on the sensitivity of the current needed. The range is 1 to 4A, each step is 0.5A. Multiple current setting ranges exist for this relay based on needed sensitivity and accuracy, ranging from 0.025 to 0.1 max. Each step is max tab minus min tab divided by 6. To 4 bars, and each step was paid by the fine bar. I have multiple current setting ranges for this type of relay based on the required sensitivity and accuracy, with relays ranging from 0.025 to 0.1 as a maximum. Each step can be calculated by taking the maximum tab value minus the minimum tab value and dividing by 6. In the relay shown in the picture, the minimum tab current setting is 1 amp and the maximum tab current setting is 4 amps. We can calculate the step by taking 4 minus 1, which equals 3, and then dividing by 6, which gives us 0.5 for each step. It equals 0 amp for each step. It's a good day, and it's a good day. To protect the transformer, we connect all the secondary CTs for the area to be protected and then send them to the high impedance relay, which is connected in series with a stabilizing resistor as shown in the picture. We assume that the type of high impedance relay used is a current calibrated relay. The voltage that appears at the relay terminals during any external fault, which is called V relay, will equal the value of the current I1 coming from the secondary CT1 at the moment of the fault, which can be found through short circuit calculation multiplied by RCT1. Calculations that times 1 RCT, where RCT1 is the CT1 winding resistance, while RL1 is the lead resistance. This includes the wire resistance to and from the relay. RL1 can be expressed as 2RL. V relay is the product of IR and the series resistances. Substitute V relay from the first equation into the second. V relay tzard I1, fault current, RCT1 plus RL1, hard ILR1. This resistance includes the wire. RL1, Ja 2RL. V relay, Ja IR, Ja relay plus stabilizing resistances. Substitute V relay from the first equation into the second. V relay, Ja I1, RCT1 plus RL1, Ja ILR1 plus RL1, Za RLR, Za RLR. Both equations are supposed to give the same voltage value because the circuits are connected in parallel, and it's known that the voltage in parallel remains the same. We can substitute the value of V relay, or the voltage at the relay terminals, from the first equation into the second equation, where we say that V relay equals I1, which is the current flowing at the moment of the fault, multiplied by RCT1 plus RL1, and equals ILR1, plus RL1 after RL1 equals RLR equals RLR. And this is the current flowing in the relay itself multiplied by the equivalent resistance. This R is the total resistance of the relay plus the stabilizing resistor. Therefore, we can express the equivalent resistance, or R equivalent, as IL1 multiplied by RCT1 plus RL1 over ILR. As we mentioned, this is the relay resistance plus the stabilizing resistance. We can calculate the value of the stabilizing resistance that needs to be connected in series with the relay directly from this equation. We told you that the equivalent resistance is the sum of the relay resistance and the stabilizing resistance. Therefore, the stabilizing resistance equals the equivalent resistance minus the relay resistance. And as we told you, the equivalent resistance equals R1 plus RCT1. Theoretically, when an external fault occurs, the current going to the relay should be 0. However, the worst case scenario is that there could be an external fault that causes one of the CTs at one end of the relay to enter saturation. If the CT enters saturation, this means that the secondary electromotive force will become 0. We can represent this situation by placing a short circuit on the CT secondary, and we must ensure that the relay remains stable during this external fault. Even if one of the current transformers enters saturation, you'll notice in this picture that the current I1 generated from the secondary CT at the moment of the external fault will have two paths to return to its source, either through the high impedance relay or through the short circuit. Of course, most of the current will flow through the short circuit as if there is only CT1. Voltage at relay terminals equals R1 more RCT plus RLL. Adjust relay impedance so voltage setting is greater than generated voltage. If voltage setting is less, relay may operate during external fault and CT may saturate. Voltage setting must be greater, so IR in R equivalent, I1 in RCT plus RL, R equivalent, I1 IR, RCT plus RLL. Since the voltage setting exceeds the voltage relay, then IR in R equivalent exceeds I1 in RCT plus RL. R equivalent exceeds I1 over IR times RCT plus RLL. Plus RL, ensuring stability by raising voltage setting above voltage relay at relay terminals. Bring external fault saturation. Since R equivalent equals R destabilizing plus R relay, the destabilizing resistor in series with the relay must exceed I1 over IR times RSCT plus RLL. To ensure high impedance relay stability during CT saturation at an external fault, increase the voltage setting above the voltage relay at the relay terminals and choose an appropriate R stabilizing value to prevent relay operation from CT saturation current. The relay's initial operating current during an internal fault should be at least 15% of the lowest expected fault current, calculated as relay operating current equals N, city ratio, times ILS, relay operating current, plus N, number of parallel CTs, times ILE, magnetizing current. In addition to selecting an appropriate value for the R stabilizing resistor, we ensure that the current generated from the occurrence of city saturation going to the relay is not capable of operating it. The initial current required to operate the relay at the moment of an internal fault should be at least 15% of the lowest expected fault current value, which can be calculated from the following equation, where the relay operating current equals N, the city ratio, multiplied by ILS, the current at which the relay operates, plus N, the number of current transformers connected in parallel, multiplied by ILE, where ILE is the magnetizing current. Magnetizing current is crucial. CT must, and perhaps the CT does not enter saturation, while the relay does not even sense the internal fault at all. So it is necessary to choose the CT with a voltage point such that its value is greater than double the voltage setting. Sometimes a voltage setting resistor is used connected in parallel with the relay circuit to increase the voltage value. The value of the operating current at that time is the sum of the current flowing through the setting resistor plus the current flowing through the relay itself. As for using the metering resistance, or what is called the linear resistance, as we mentioned before, it is used to determine the voltage generated due to the high impedance relay during an internal fault. The high resistance will generate a high voltage at its terminals, like peak voltage, which affects the wires and the relay and may exceed their insulation limits. Typically, the metering resistor is only used in cases where the peak voltage at the relay terminals during an internal fault exceeds 3,500 volts peak, and in some references, 3,000 volts peak, depending on the type of relay used. The expected peak voltage value at the moment of an internal fault can be calculated using this equation, which references that this equation was derived from practical experience. Here, V peak equals 2 multiplied by the square root of 2 multiplied by V knee point of the CT, multiplied by V max voltage, where V knee point of the CT. This equation is used if the value of the CT is 100 V, and Vk is less than V volt divided by 2. However, if Vk is much less than V volt, which is the voltage generated at the relay terminals during a fault, another equation is used to simplify finding the value of V peak, which is as follows. V peak will equal 2 multiplied by the square root of 2 multiplied by Vk and V volt. To the key and the voltage. As for Vf, it equals If secondary multiplied by RCT plus 2 times RLL plus the stabilizing resistor. Notice from this equation that increasing the value of the CT resistance and the wire resistance will increase the value of Vf. Consequently, an increase in Vf will lead to an increase in Vb. Thus, we will approach the limits of the relay coil's insulation breakdown. It is usually recommended to reduce the wire resistance by increasing its cross-section as R equals R over A. So, if the value of A increases, the value of R will decrease. The metering characteristic can be expressed using this equation, where V metering equals I metering raised to the power of beta multiplied by C. Beta and C are constants that vary depending on the type of metering used. This table shows some types of metering that can be used along with the values of the constants C and beta mentioned in the equation, in addition to the value of the relisting and its details. If the secondary circuit is accidentally opened during maintenance or testing, it will cause the emergence of unbalanced current flowing through the relay, metering device, shunt resistor, and the magnetizing impedance. This current will lead to incorrect operation of the protection devices in two cases: load and threefold condition. Of course, depending on the value of the secondary circuit set, it operates at 5 or 10 volts. If it equals 10% of the lowest load current on a parallel circuit, it waits 3 seconds before activating. This ensures the relay and impedance resistance are not damaged by voltage from the open secondary circuit. The supervision relay sends a signal to the cascade indicating the protection device is in fault condition. The 3 seconds prevent incorrect operation of the supervision relay due to unbalanced current. I have suffered a lot and a lot of trouble. To prevent the relay and the impedance resistance from being damaged by the voltage generated from the open secondary circuit, the supervision relay must send a signal to the cascade to inform it that the protection device is in a fault condition. The reason for the 3 seconds is to ensure and avoid incorrect operation of the supervision relay due to the unbalanced current resulting from the situation. Supervision relays like NVTB31 or VTX31 are used. Opening CT1 circuit causes current I1 to flow through magnetizing impedance ZM2 and ZM3 plus relay resistance R relay and R hysterizing. Voltage across the supervision relay V supervision equals R1 times RRZR for stabilizing in parallel. It's ZM2 and ZM3. Let's clarify with examples. If external fault current is 10 Ka, CT ratio 400.1, relay winding resistance 3 ohms, and CT cable resistance 2 ohms, magnetizing current 30 mA at 150 volts, and relay pickup current 20 mA. What is the required relay voltage setting? If the external fault pilot value is 10 Ka and the STI ratio is 400:1, while the relay wing resistance is 3 ohms and the total resistance of the STI connection cable is 2 ohms. The magnetron current of the shaft was 30 milliamps at 150 volts and the relay pickup current was 20 milliamps. What is the value of the relay volt setting required against the relay at that time? 1. What is the minimum pickup current that can be used? 2. What is the required knee point voltage for the current transformer? First, we calculate the voltage appearing across the relay at the moment of the external fault, and then we multiply this value by 20%. As a factor to determine the relay pickup setting voltage, the voltage appearing across the relay terminals during this fault will equal the primary voltage divided by the CT ratio. To convert this value to the secondary side, and then we multiply it by RCT plus RL. Therefore, the fault current value is 10,000. The division is 125V, determine voltage setting 20% higher for safety. Relay, setting voltage for 1.2, calculate minimum pickup current I for M, CT ratio 400.1. Voltage is 1.2, calculate minimum pickup current. I to 401 x 0.02 plus 2x 0.03. Now we calculate the required operating current where I, M, the CT ratio, 400:1 x ILS, the current needed to operate the relay, 20 milliamperes or 0.02 plus N small, the number of current transformers connected in parallel, 2 times ILE, the magnetizing current, 30 milliamperes or 0.03. Thus, therefore, equal. The required value to be installed is as follows. It should be greater than or equal to 2 times the previously found value, which equals 150 volts. Therefore, it must be greater than or equal to 2 times 150, which equals 300 volts. It has been previously found that the voltage equals 150 volts, so the CT of 100 volts must be greater than or equal to 2 times 150, which equals 300 volts. Is a metering device needed? With 10 kiloamperes fault current and CT ratio 1000.1, check necessity. Set voltage equation. R secondary voltage, X, RCT plus 2RL plus R stabilizing. Calculate relay resistance. 150 volts, 20 milliamperes, or 7500 ohms. Other resistances are negligible. Voltage, I secondary voltage X relay resistance, where I secondary voltage of 10 kiloamperes, CT ratio 1001, X 7500 ohms. Voltage is 75 kilovolt. The relay pickup current is 20 milliamperes. So, is it necessary to use a metering device or not? The first thing we do is set up the voltage equation, which equals R secondary voltage multiplied by RCT plus 2RL plus R stabilizing. Then we calculate the relay internal resistance, where the relay resistance equals 150 volts divided by 20 milliamperes, which equals 7500 ohms. Here, we can neglect the other resistance values because they are very small compared to 7500 ohms. We can say that the voltage will equal I, secondary voltage multiplied by the relay internal resistance, where I, secondary voltage, is the 10 kiloamperes divided by the CT ratio, which is 1000 to 1, multiplied by 7500 ohms. Therefore, the voltage value will be 75 kilovolts. Since the value of CT my V, which is symbolized by the symbol Vk, is equal to 400 V, which is much less than the value of Vf, which is equal to 75 kV, we use this equation, where Vb is equal to 2 times the square root of 2 times Vk times Vf, and Vk is 400 and Vf is 75,000, so Vb will be equal to 15.5 kV. 400 and Vf 75,000, so the O will be equal to 15.5 kV. Even though the value of Vb is more than 3000 volts, the use of a metering device becomes necessary and mandatory here. Another detailed example with calculations for a bus bar of a certain type is provided, where the requirement is to find the value for the first bus bar, in addition to requirement to find the R stabilizing for the 3-zone main 1-hole discrimination zone for the second bus bar. The required thing is find the R stabilizing for the 3-zone main 1-hole discrimination on the first for the second bus bar, in addition to the... In this example, we will notice that each zone has more than one loop resistance. Therefore, we calculate the loop resistance for each path and then select the maximum loop resistance among them. This is certainly because the higher voltage will drop across the higher resistance. Thus, the relaying voltage will equal the secondary current multiplied by the loop resistance, where the loop resistance is the maximum loop resistance. After finding the value, we then calculate the value, which equals, as for the relay chosen in this case, its resistance is 3500 ohms, while the current needed to operate this relay is 30 milliamps, and thus the voltage across the terminals of this relay will equal 30 milliamps multiplied by 3500 ohms, which will equal 105 volts. As for the series stabilizing resistor that needs to be installed, it can be found using these calculations in 2 ways. Either we say it is the voltage across the stabilizing resistor itself divided by 30 milliamps, which is the current needed to operate the relay, or we can say it is V setting divided by I setting minus the resistance of the relay. Usually, it is confirmed that the stabilizing resistor has been set correctly in 2 ways, either by measuring it directly with a multimeter or by applying the V setting, which in this case is 130 volts, and then adjusting resistance value until the current drawn reaches 30 milliamps, which is the current needed to operate the relay. A value can be calculated by finding a value, then finding a value, then finding a value where it is equal to this. Hence, the value of the land came where it is equal to the sun's generosity. The total operating current is the sum of currents from the supervision relay, high endurance relay, city magnetizing, shunt resistance, and metro cell. Adding metro cell current to the total operating current involves finding its value from an equation, but it's often negligible. For metering cell testing, apply AC quality, measure current with an ammeter, and compare with equation-derived values. This traditional method contrasts with CPC 100 testing mentioned in episode 10. Follow previous steps for Zone 1, Zone 2, and check zone settings. Detailed high-impedance spiral protection calculations for these zones are available for independent study. Most calculations for lines, transformers, or buses use a pre-made Excel sheet, an example of which is attached. This concludes today's lecture. Join us for the final episode on stability and sensitivity test for transformers, lines, and buses. See you soon. Peace be upon you. We apply the same steps we mentioned earlier when finding the settings for Zone 1, Zone 2, and the check zone. We have done detailed calculations for the high impedance bispiral protection for Zone 1, Zone 2, and the check zone, which you can study independently for more information. Most of the required calculations for lines, transformers, or buses are usually done using a ready-made Excel sheet, and we will provide you with an example of this Excel sheet in the attachments. With that, we conclude today's lecture. Join us for the next and final episode, where we will explain the stability and sensitivity tests for transformers, lines, and buses. See you soon. Peace be upon you.